I am presenting the paper Transforming Natural Language Specifications to Logical Forms for Hardware Verification. Modern integrated circuits are packed with multiple complex modules and IP blocks to meet the demand for increased functionality and performance. At the same time, due to aggressive time-to-market constraints, the overall design lifecycle has been reduced. As a consequence, complex hardware systems are being developed at a rapid rate, but it is becoming increasingly difficult to verify these designs. This situation continues to worsen even after spending more than 50% of the time of the project on verification. As shown in this graph, taken from 2012 Wilson Research Group Functional Verification Study, in some projects, even more than 80% of the time is devoted to verification. The verification task that takes most of the efforts is the debugging work. Assertion-based verification is commonly used technique for debugging. In this work, we are automating the assertion-based verification from natural language specification. Automatic generation of assertions from specification documents have the advantage of reduced time to market, early identification of incomplete and inconsistent specifications, and reducing number of design errors. Here is the block diagram of our proposed approach. Input specification passes through chunking module where it is split into smaller phrases. Then, using dependency grammar, the phrases are passed using transition-based passing algorithm. Output is a frame if input is a high-level architectural specification. If the input is a low-level assertion that has all required variables, then we can generate system Verilog assertions at the output. The underlying principle of our parsing framework is to view each specification as a collection of semantic fragments. As shown in the specification here, the specification consists of words from W1 to W7, and it consists of two semantic frames, frame 1 and frame 2, that are connected incrementally, and the overall specification is understood. We have created a semantic grammar for hardware verification domain. The semantic grammar describes when and how frames and slots are filled. For example, the implementation of first row in the table is illustrated with a diagram below for the phrase equal to 1. So when the edges for this phrase equal to 1 are created, the relation frame at word equal is filled by value 1 at slot relation object, and this slot relation object is considered as a semantic destination of the value 1. We evaluated our framework on both RTL and architectural level assertions written in English language. We picked 90 RTL specs from AMBA 3XA protocol, and we successfully translated them to system Verilog assertion. One such assertion is a value of X on AW_len is not permitted when AW value is high. Then we tested our framework on high-level specifications, and for this testing we picked ACE and ACE-LAT protocol specification document and took 4 channels of this protocol document. So these 4 channels contain 34 high-level specifications, out of which we translated 22 high-level specification into frames. One such specification is clean invalid, clean shared, and make invalid transactions must not be system shareable. Then we manually wrote specifications of UART and memory controller and successfully translated 80 such specifications. One such specification is when command active occurs, then command precharge should occur before 12,000 clock cycles. In this work, we have developed a semantic frame parser to generate logical forms for hardware specifications written in English language. The output of the tool is in the form of frames and are machine readable. In future work, we would like to enhance the tool with the ability to handle both extra grammatical and ambiguous specifications. Thank you.